we have been talking about binary, and life does not just exist as binary cases. There will always be that complexity, and also multi-class issues could arise. So a bit of deviation to a multi-class data set. Going backward now into some of the exercises we have looked at, examples we have looked at previously, we have talked about so many interesting data sets. However, I don't think we have talked about the wine dataset. So that's why I brought up the wine dataset. It's also gotten from the UCI machine learning repo. It is a multi-class dataset problem that has 3 classes. And these 3 classes were based on chemical properties of wine. So the objective is for us to predict the class of wine. And if I'm not mistaken, if I remember correctly, I think it means either a good or something bad or poor wine. I couldn't remember that, but I remember doing that some time ago. But we have class 0, class 1, and class 2 based on the chemical analysis. So it has 13 numerical features, which include alcohol content, malic acid, ash, magnesium, flavonoids, phenol, and others. And the data size is not that big, it's very small, around 178 samples. So they commonly use this data set for classification, problem, feature analysis, and also for interpretability studies like we are doing now. So what we're going to do, again, this data set can be found in scikit-learn dataset. So let's just make it very easy for us to call. So which is what we're just going to do now. So we call it, again, it's good for us to make it a data frame so we could be able to do some EDA. So again, the next thing is for us to look at the head of this data set. So just to have a preview of how these data sets are distributed. So again, it will make sense if we can look at the info. We can actually see from here all the data set except the target variables are all float. And then another interesting part we could see is that all of them, there is no presence of missing. And then when we looked at the summary statistics, we could actually see interesting descriptive stats like the mean, standard deviation, and so on. Again, let's look at the target variable to see if there are cases of imbalance. Not much, although they exist, but we have around 71, 59, 48 belonging to each of the classes. So if we make a plot to see it much better on visuals, you could actually see there are some imbalance in the class distribution, but not that much, although in class 2 is a bit of underrepresented in the dataset. So now, again, it will make sense if we plot the future, the heat map, the correlation heat map to see if we have anything around multicollinearity. Yeah, I could see we did have something around total phenol and flavonoids. There seems to be. And then another thing again, if you could notice, I slant this axis. Now, the reason I slant this axis is because when you're plotting, sometimes you want to have a view of how these plots look like. If they are straight, they could take a lot of space. And when you are reporting, it's difficult. And also it makes it difficult for your audience to follow with their eyes. So you have to make sure you make it convenient for them. Then another thing again, when you slant it, you will discover that sometimes when you slant, you have to be careful because it could misalign. It means it could easily shift out of the plot. This is what I mean when I said it could misalign. So probably I could show you guys. Oh, okay. Yeah, you can see when you slant, can you see there is an overlap here? This one, can you notice? I don't know if you noticed this. Can you see this misalignment? So you have to make sure it's aligned well. So make sure you put this high right so that it's fall in place. Okay. So take notes of that when you're slanting. So now you can see it has gone back to our proper alignment. Okay. So take note of some of these things, because when you are making visuals as a data scientist, nobody will excuse you as an expert. People can easily raise some of these things. So take note of this. However, another thing I noticed in this plot is that this data set here do not make sense. Sorry, this column or variable here do not make sense. It seems to be complex for me or even anybody, an audience. So it makes sense if we can rename this data set here. So we have to think of some sort of a future engineering on how we could take care of that. So what we are going to do, in order for us to do that, we have to look at where that column is in the data set, which is here. So we have to give it another name. So we are renaming it to ratio, because if I could look at this, looks like a ratio. So we just call it ratio dilute wines. So now we have done that. Now, by the time you do that, if you go back and say you visualize this, you would see that it's you will see some changes. Okay, good. So you can see this has reduced to ratio dilute wine. So you have to be sensitive to some of these changes. So the next thing, we can also see if it has, so it has changed to ratio dilute wine. Another thing again, we want to see if there are some relationship or potential outliers between the alcohol and the target. So interestingly, we could see a bit of an outlier up here, but it's fine. We can see they all distribute fine. So now we can go into the modeling phase, like I always say. So we can go into modeling phase. Before I go on, do you have any question? So I don't just keep you guys. Probably you want to ask questions. So anybody that has question, that wants to ask any question, feel free.
Yeah, I actually do have so many questions.
Okay. Go on.
All right, thank you. It's quite an interesting class. So now I was like, okay, first of all, how do you measure the collinearity, the feature collinearity? Like, I still want to understand the science there. How do you know what I think you explained in the last class, but maybe I didn't. I probably maybe I'll get better again. Like that there is this here. This is not the whole essence of the heat map, and then you get the feature collinearity that's talking about.
Okay, so normally the collinearity is, you see, when you are looking at the heat map, these diagonals here, it's fine. We expect them to be 1.0, 1.0, because it's correlating that variable with itself. So this one here, for example, is correlating with itself. So definitely we will expect it to be 1. So this as alcohol here correlates with itself is 1. Now, but when this alcohol correlates with this malic acid, it said it's 0.09. So this is a weak correlation. It means that both of them are not competing against each other. They are just coexisting, or they are just existing. For example, when it correlates with ash, you can see around minus 0.31. So it's kind of very weak negative correlation. Then here, when it correlates with alkalinity of ash, we have around 0.27 and so on and so forth. However, when you come to this place here, this total phenol, when it correlates with all that, you can see 0.34, 0.3, and so on and so forth. But when it came to this point here, this is where it correlates with itself. But when it came here, it correlates with this flavonoids. You could see 0.86. It means that both of them are competing against themselves. So this 0.86 is high. Now, some cases, you put a cutoff around 0.8. You say any value above 0.8 is high. It means there is a presence of multicollinearity. They are fighting each other. So because they are fighting each other, you would say it's better we drop maybe total phenol or flavonoid, we drop one, or we find a way to create some sort of maybe future engineering that will add them together or something to become one variable. So either you'd remove it, you find a way to deal with it, or then, and again, like I said, if it's not an important thing in that task, you leave it out, because we don't expect these futures to be in isolation. So if, for example, we don't have so much futures in this case, but remember, if I'm having maybe like 1,000 futures, I would definitely want to screen out so many futures out so I could have the best futures as possible. Do you understand? So that kind of situation, I would look at when I see 0.86, one of them will go. Or I think of how I can merge them or something, like that. For example, you could also see around here, we have 0.57. This is not that strong. This is cool. We even have 0.65 somewhere here. It's also fine. So what you are always looking at is this adjacent here. This diagonal, you look at this one and this one, this one, this one, this one, this one. Here you are looking at this one and this one. Here you look at you always be looking at what they are correlating with. Are they fighting each other? This one and this one, this one and this one, this one and this one. So this is what you are looking at. So each time you are looking at the plot, looked at the adjacents and see, then you will figure out if they are competing with each other. So that's how you spot them. So once you spot them, if it's greater than 0.8, it's a red flag. There are some cases if you can even set it to 0.7. You say if it's greater than 0.7, it's a red flag for you. You can remove it. So like this case here that we have around 79, you will say definitely one of these, should go or something. So that's how you spot the multicollinearity thing. But like I also said, it's not all cases, because these decision tree models learn to deal with this thing, except if they are highly correlated. But if it's a case where we have one or two features that are struggling with each other, it's learned to deal with them. But if they are so much, like maybe 80% of the features are highly correlated, then you would have a problem. So, but if the percentage is very low, the model, the algorithm will find a way to handle it. It won't be an issue for you to struggle with. But it's good for you to also, on your own, you can remove them and run the algorithm to see if it's actually improved the model or not. Because sometimes they will not improve the model, they'll just be fighting themselves. You see the thing, it's funny example, but it just dropped my mind. When we were growing up, there is this people that we don't like to put them in football, because when you put them in football, they would not score goal, they will not do anything, they will now be even struggling with you, that we are the same team, and that person will be struggling to remove ball from my from your leg. and stuff like that. So it's kind of the same thing. That future is a Bayesian in your future set. It's not predicting, it's not helping to tell us anything about the prediction set, but it's fighting the other futures that will tell us something about the prediction set. You understand? This kind of futures behave like APC. They don't know how to fix Nigeria. They would not allow people that will fix Nigeria to fix Nigeria. So stuff like that. So it really like we have so many multicollinearity in actions. Anyway,
very clear.
Yeah, so that's how you spot them.
So, but if your features are many, like we have like 1,000 features, high data set, do you think this heat map will be possible?
No. You don't use heat map in that case. What you do is you run them and output it. So what you can do, you can run it instead of plotting the heat map. You convert it to data frame, and then save it as CSV file. And then you can open it and check the correlation coefficient for them. Or you can even automatically write the algorithm to sort out those ones with high correlation and output it for you. Then you can now study them. I've come across this kind of situation when I'm doing genetic and handling genetic data set. So what I normally do, I don't visualize when they are much. I just output them, and then I look at the output and see how do I now deal with it. Then the ones I don't need, the ones I can merge, then I merge them. Then there is also another approach called variant VIF, variance inflation something. I've forgotten the full meaning, but the VIF help us to also deal with this multicollinearity. In fact, the VIF should be the measure that we use to handle this kind of thing, because it will identify the futures that has issues with the multicollinearity, because it has a sort of a cutoff already. So on your own, you can look at the VIF and see. So you can write multicollinearity
like
using
various inflation factor, doctor.
Good. Variance inflation factor, yes. So it helps you to deal with that multicollinearity issue. And then once you handle it, you can continue with your modeling.
Good. And we were in the last time when we talked about the feature selections, so you're using the PCA and the other method of feature selections, where you need to, where you will not use all the features, where you will not need to use all the features for explainable purposes, for interpretable purposes. You mentioned probably you were going to use that, see how we can apply that when we start talking about the explainable model.
Yes. Yeah, you're correct. For me, okay, maybe when we start this class, I could talk about that. I think I did have a step on explaining that. So probably we were a bit faster than. So let's leave that to when I come to it. Because, for example, it doesn't make sense in SHAP if I have 200 futures or even 1,000 futures. It doesn't make sense for me to display all. In fact, the SHAP will not make sense. So what I'm going to do is to select maybe the top 20. You understand? The top 20. Because most of the time, even the future importance, when you display all, you will see that majority of the futures will not be more than maybe 20, 30 that are really pushing the prediction forward. So instead of focusing on everything, you just focus on those ones, and then you'll be able to handle it. The manuscript I told you guys I was working on yesterday, it's the same kind of issues like this. It's not that I can't show you guys because it's still something we have not yet released. But the moment the manuscript get out and to reviewers and all that, I could show you guys how it's very, very interesting stuff that I did there. I have about 1,100 futures. And these futures were ICD-10 codes. So I needed to know which of the features are much, because that when you looked at the matrix, it's a sparse matrix. So that kind of sparse matrix will definitely be suffering from cost of dimensionality. So I needed to find ICD-10 codes that are much consistent. So I used some feature selection techniques. So with those feature selection techniques, I was able to get the most consistent features. So the moment I got most consistent features, I reduced that big matrix that had 1,100 features to only 283. So with those 283 features, I now started doing my modeling. So remember, even the 283 are super large. So when I came to my post in model interpretation phase, I cannot be displaying all these features. So what I did was to focus on the most resilient top 20 features. So when I did the SHAP for all of them, I asked it to visualize for me only the top 20. Then when I also did some domain interpretation techniques or explanation approaches, I worked with those 20 features. I didn't work with all those 282 features again. So that's what you do, because you cannot really, the world is very, very complex. And the more you increase the complexity, people lose interest. So you need to make your audience to be interested in what you are doing by simplifying the complexity of those things. So always think about when you want to do the explanations, reduce it to such a way that it will be minimal and everybody can follow. For example, the binary case we just displayed not too long here, the reason we all could follow this is because the features were not much. We just focus on the few features we have. It's easier for anyone to look at this and understand. But the moment they are much, you lose that focus. You will not be able to follow what is happening. So I think in the next this thing, I'll be able to show you guys how to select just few of them.
Thank you. Just one more question, please. Sorry.
Okay.
In the binary classification we just did, when you look at these features, when you pick the samples of the patients, individual samples, the features, certain features contribute to making a particular patient positive. And then when you now look at the explanation of the other patients, same features are the one contributing to make the patient negative.
Yes.
So I think I'm a bit confused. So what exactly is it telling us? Why is this one negative, but using the same feature, it's negative? This one uses the same feature. So I'm really a bit confused.
Okay, so you don't need to be confused, Bondi. You just have to understand, you say all of them are measurement. It's just like when people go to check, for example, you want to run blood tests, the doctor will collect your sample, the same sample that they will collect, let's say urine and probably blood from me, they will collect it from any other patient that comes around. But what is going to change is the measurement. Do you understand? It's the measurement. For example, now, is there a presence of Plasmodium parasite in that person's blood? So the moment if you see it, it will definitely maybe increase some measurement in that person. For example, in the case of this cancer, you will likely see maybe some tumor. The size of those tumors. So the same people will go to run that test. They may have those tumors, but those tumors are not cancerous. So there are measures that the doctors are looking for, but the same measurement they will collect for everybody. I don't know if you understand. So what we are looking at is the value of that measurement. The value of that measurement. So the same measurement for different values. So if the value is heightened in some persons and is very low in other persons, then it signifies something is happening. Like chronic kidney disease that I am working on as well. When you are looking at from control group down to end stage, you will see that there are some biomarkers, some urine biomarkers, you will see them, they are increasing steadily. So you will see in the control group, they are very small, but in stage 1, you will see they are a bit heightened. When you move to stage 2, they are a bit heightened. When you move to stage 3, you will see they increase. Stage 3A. When you move to 3B, you will see they'll just skyrocket, like to just go high. Then when you move to 4, you will see they will just go on the extreme or something. So that's the same measurement taken even in the control group, but it's the value that changes that we are looking at. So that changes of that value is what raised the red flag for us to begin to see. That's why when you go to the hospital, you run those tests. When the measurement comes, the doctor will be looking what makes this patient diabetic and what makes this patient not to be diabetic, or what makes this patient to be hypertensive. And what that's why you see people will be checking even their weight. You go and check your weight if you are obese or you are overweight and all that. All those things is the same weight we are checking, but it's the measurement that triggers for us to know this person is obese, this person is underweight, stuff like that. So same measurement, but the values changes, and it's that changes in the value that tell us the status of that patient. So you could see the same measurement that we take for this person that is cancerous, the same measurements are pointing to different direction. So these values here, for example, for this worst area for this person is minus 0.35. Now, let's look at this value in someone that do not have cancer. Can you see 1.74? But when you look at worst area, it's minus 0.35. So it means this value tends to be becoming smaller in patients that have or developed the cancer. Maybe some sort of deterioration happening in those as a result of the tumor, and in somebody that is normal, we could see these values are high. This is 1.74. The worst concativity is minus 0.03, but you could see for somebody with cancer is minus 0.04, which means that the worst concativity is not really what is detecting if somebody has cancer or not, because we could actually see that the elevations are not that different from both. Someone without cancer is minus 0.03. So it's not really a red flag. That's not really maybe what tells us. But what's beginning to tell us is when we looked at ranges of values and they are consistently decreasing, then when we look at them in a control group, they are heightened, then we know that something is wrong. These two patients are different. Do you understand? So like in the work you are doing, you can, if in the case of malware, let's say you want to know if what is making this particular I don't know, variants, or let's say I think it's variants. If I use variants, I think I'm correct, right? A particular variant of a malware, what makes it to be that different from another malware? It's when you now begin to look at how those features are maybe popping up, heightened, or averaging in that particular, maybe the API calls, for example, you're looking, and then you discover that there is a behavior that the measurement that makes that malware to be variant is really different from another kind of malware. Then you will now draw the attention of experts to say, let's look at it. Something seems not adding up here. Then the experts now could begin to look at it and say, yeah, this is not how it's supposed to be, because all these things have a standard or an SI unit. For example, in the medical domain, there is a particular standard that you know that if this thing exceeds this standard, then this person is hypertensive. So the moment you see a value going out of that range, you begin to tell that person, you need to do this, you need to do this, you need to watch this, you need to watch this, you need to change your diet, you need to do. You begin to, tell them what to and what not to do, and some of them even have to place them on bed rest. Yeah, I don't know if you understand. So there is an established this thing, and it is your duty as an expert in that field to know them. So if you take these things to a doctor or a pathologist or something, they could easily interpret it because they know these things. It's something they are used to. They are expert. Just like if you bring descriptive statistics to a statistician, he doesn't struggle to know that if that variable is normally distributed, if that variable violates some certain assumptions, if that variable is statistically significant, all these things are inbuilt because you have, as a statistician, you have been trained in that field to know them. So the same thing, a doctor too is trained in those fields to know them. So what you do, that's why we say don't work in isolation. Always try to have the input of domain experts, because the domain experts will help you to point out these things, and they will help to give you direction on what to do. Anyway, we're running short of time, so I don't know if I answered your question, but let's see if we can finish up with the multi-class. Did I answer your
Very
question?
clear. Very, very
Okay.
clear. Thank you.
Okay, great. So I think this is where we are, the modeling phase. So quickly we run the target, we split it again into training and testing, then we scaled. So the next thing, we are going to train also the random forest using the grid search, and then subsequently we're also going to train the XGBoost. So yeah, it will take some time, of course, because we expect that the grid search will always take time. So interestingly, let me just go for the best model here as well. And then let's see what happens. Good. So it has finished running, and it comes back to tell us the depth is none, the sample point is 2, the estimator is 100. So let's evaluate, and everything seems to be 100. But like I said, this data set is very small, so I did expect some overfitting. So I wouldn't trust the random forest. But again, like I said, when you look at this kind of problem, it's already been established that over and over again. So it's kind of very well known. But this 100, try to re-examine it. It's in real life, it shouldn't be always 100 like this. It's not Uhuru, eh? So always check out those things. Anyway, let's see the future. So you could see in the future importance, we are only focusing on the top 10. Okay, so on the top 10, we have the flavonoids, the color intensity, the proline, and so on and so forth. They are the top features from random forest. So let's also look at the AUC. So the AUC in the multi-class is different. It's not the same like the way we do the AUC for the binary. So what the multi-class does is that it will check it against each other. So if you have 3 classes, one class will act, it will behave like a binary. So it means one class will act as a sort of a baseline against another class, act as a baseline against another class, act against, so it will be testing against another class, testing against. So you will see us using something as one versus rest classifier. Sometimes it's one versus all. So depend on the ones you pick. Now, because the machine learning will still be treating it as a binary, even though it is a multi-class whenever you're doing. Because if you don't do that, you will not be able to get the predicted probability, because the area under curve is just telling us the area we are sure that we are getting right. So that's why we're using this one versus rest. So each time we have a multi-class, it changes. It's not going to be the same like we do when we have binary class. So again, you can see we are having a perfect fit. Like I said, always a red flag. I don't feel comfortable because the data set is very small. So of course we did expect, but of course in real life you wouldn't have this 100%. So let's also look at the training with XGBoost to see what we are going to have. So again, we fix the XGBoost with the grid search, and then we predict again. So the XGBoost showed the learning rate to be 0.1, the maximum depth to be 3, and also the estimators to be 100. So again, we are going to evaluate. So a bit of decrease in XGBoost, but we still see quite a very high score. But I think I'm much more comfortable with the XGBoost, even though the random forest seems to be overestimating or overfitting the problem. So but let's stick with the XGBoost for the explanation. So again, we will look at the future importance from the XGBoost. So when you looked at in the XGBoost, again, we could see there is some discrepancies between their futures. So we could see flavonoids was the top future, but in XGBoost, flavonoid was the fourth. So 1, 2, 3, 4. It was the fourth future. Then we also see ratio diluted wine actually moved up to be the most important feature in the XGBoost. So again, let's look at the AUROC curve. Again, we still have a perfect fit. Like I still said, it's not always Uhuru in real life. So we did expect to see some. So I do expect to see some sort of a very nice curve, not this perfect fit, but again, this is an example. So we take in the best future. So now we want to do the post hoc interpretation, but it makes sense if we can build it in the data frame. So we can be able to, because this is a multi-class problem. So we have to be careful, if we want to make the visuals. So that's why you see that I converted the dataset back into data frame from NumPy array format. So by the time you run this, you also now put fit in wrap it around the SHAP explainer. Then the class name, remember we have 3 of them, 1, 2, 3, wine. So let's run the SHAP to see what we are going to have. Good. So this is for the first class, which is class 1. We can see now if you look at the SHAP, I requested now this answered Monday's question. So I requested for the 10 top futures. In this case, not 20. I request for the 10 top futures. So because we have lots of futures, and I wouldn't want to be struggling with all of them. So just the 10 are okay for us for the SHAP. You can decide, you can play around when you are running the script, maybe move it to 20 or something, but we are just focusing on the top 10. So for the first class here, you can see the proline, how these features are pushing forward or backward, depend on, again, the directionality, but we could see the majority is around proline, flavonoids, and alcohol. They seems to be the top, and then maybe a bit of ash. Then on the second class, we see color intensity is a factor. Proline, alcohol, magnesium are also a factor in the second class. Then in the third class, okay, and then this is. So in the third class, we see that there is a decrease. Flavonoids, color intensity, diluted wine, and whole are actually the most important. So you can see each of the class have what is driving them. And they are not always the same in each class. Now, let's see what LIME is going to tell us. So we are building the LIME for the multi-class problem again. So we run the LIME. Like I said, you first build the local explainer, and then you perturb it around the complex model. So now we're doing that for the complex model, which we have just done now. So the next thing we are going to now do the explanation to see what we are going to get. So, yeah, this is a bit hanging. Okay. Okay, good. Yeah, so that's run. So now let's see what we have here. So we pick now, of course, we pick one instance here. Remember, we pick one instance. So let's look at this one instance that we pick. So for this one instance, it is actually 100% sure that it belongs to the class 1. So now let's look at which features are colored, are yellowed here that makes it to think it's class 1. We could see color intensity, proline, alcohol, malic acid, ash, magnesium, flavonoid. It seems to be the top features. Then on the other end, we have total phenol and ratio dilute wine. So, like I said again, these things will compare them as the way binary does. So it will compare one against another, and then it concludes which one is actually moving. So let's say we have 5. Let's increase the ranges for them, for the SHAP. Then let's see what happens. So if we have 5 samples, we can see for this explainer here, we would see that it's most likely to belong to one of this class here. So we can see the features that are green are very few. On this second sample also, you could see the features that are pushing it are different from that of this feature. Then the third sample here, we saw these green features are a bit much. And then on the other samples, we also see there are changes. And then on the fourth samples, we see the green are much on this direction. However, we could see that all these samples, what is contributing to them is quite different from the other one. I think before I upload this, I'm going to include the legend so we can be able to see why it belongs to this class or it shouldn't be the other class. So, but with this, you cannot really specifically say which of the class it belongs to. But the aim is just to make you to understand which of the features are contributing to the prediction. So, entirety, when we look at this, it did make sense. But remember, we talk about the issue around dependency. Now, these approaches do not tell us about interactions. Even though SHAP has some plots we call dependency plots that we could use to check for interactions, but it only tells us interaction between 2 variables at the same time. Not maybe when you have so much of them, you can't be able to visualize them at one go as such. So it makes sense if you could deviate to something different. So here we are going to be outputting the SHAP features. And if I'm not mistaken, we have the total of, in this case, I think we have total of 13 features. Is it 13 features we have? Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 features we have. So so 13 features is quite small. It's not a problem. So we will just work with all the 13 features. So from that SHAP that we did before the line, I want us to visualize if potential interaction can exist among the features. Are they cross-talking at all with each other? Now, one of the easy way we could make this visualization is via interactive network. Now, the interactive network is very, very useful when you are looking at things like social media. In fact, interactive networks can really pinpoint to us where a particular signal is emanating from and where it's actually heading to. So, like, for example, if we want to track a fraud that maybe somebody wired money from one account to the other, most of these terrorism financiers or financiers, they don't use a direct, it's not going to be a direct wiring. Maybe what they can do when, if they want to send a large chunk of money, they will split it into several accounts. And then at the end of the day, they'll transfer them to maybe up to 5, 10, 20 times before it gets the final person they want to. So that kind of approach, the network science or interactive network can help us to be able to know where this thing originated and where it finally terminates. So Netflix uses it, YouTube, Facebook use it for recommendation. That's why you see that you can, when you look at your friends, mainly people that are really, you know them, maybe they are your classmates or, you know, people around the space of your influence, and mostly people you see that the system recommends to you. So the network science is a very good way of, you know, helping us to be able to identify these interactive networks. So the interactive networks have what we call an edge, and it has what we call a node. Now, I will see if we could have a time to look at it as a whole discussion on its own, because it has different principles, it has different meaning, but the edge is usually the connecting lines between the nodes. And then the nodes are usually where that particular value or measurement starts from. But anyway, like I said, we'll have a way to go through them if I did have a time. So what we simply did for the domain knowledge interpretation, we're going to pick, let's just work with the whole setting features that we have. And then for each class, we want to output the SHAP value, because SHAP has helped us to rank them. So we want to output each of them. So we have output them, we have saved them as a CSV file. So if you see, we save them as a CSV file. So what we now do, you can actually, and then the original data set that we're working with, remember it's a wine data set that has all these features. So we want to use now we want to load the SHAP for the first class that we have from where we have saved it. So which is what we just did. Now, the next thing we want to do, we want to rank the features based on what the data frame. We want to create a new data frame, ranking them based on the future ranking we have identified from SHAP, because SHAP is telling us this feature is the most important, this one is the most important, this one is more important for this particular class. So that's what we are now going to do. So we are ranking the features based on the SHAP output that it gives us. So now we have done that ranking, and you can see for that particular class, because SHAP told us the proline, what is much important for the first feature. So the next thing we are going to do, we're going to visualize via that interactive network to see if these features are cross-talking to each other. Now, you can play around with all of them. Some of them you can turn them to red, some you can turn them to colors and all that. But now, the moment we run this, we want to see what's happening. Good. So now you can see, if I can zoom out, you can see this interactive network tells us something about which of the features are actually interacting with each other. Now we can actually see how these features are connecting. Which of them have more dense interactions? Which of them has a lot of inputs coming in? So we could see the ratio diluted wine is actually at the center. The ash is also there. Those ones at the edge, mostly they have very fewer connections around them. But you could see the ones that have lots of connections going into them, the diluted ratio wine, the ash, and then probably the proline also have a lot of connection. And also the color intensity, not bad. But you can see, so the whole aim of this is just to see what sort of interaction are going in, which ones and which one are talking with each other. So I think we have come to the end of today's class. We exceeded the time. But I think this is a good place to stop for today. I could also see in the next class how I could bring in so many domain explanations to show you how you can use this output, in different areas. So if you have any question, feel free to ask. Before I use the mic. Any question?